Okay, so this is on page 291. You've got machine 1, or machine A and machine B. You're going to throw a number into machine A. You're going to start by throwing in a 3. Figure out what comes out. And then whatever comes out gets thrown into machine B. And then whatever comes out is your final answer. So I'd like you to try these 3 on your own. And if you've done those 3 already, I'm going to get you to add one more. X is equal to -4. So this is what a composite function is having one thing happen first and then doing another thing after it. Okay? What this looks like is if we call this one function f of x and this another function g of x, what we have done is this, g of f of x. And it's sometimes written that way, and it's sometimes written that way. When it's written that second way with a little composite sign, which is like almost like a multiplication dot but with a hole in it, a little degree sign but in the middle, just think of this like this, and that'll help you. And when you have this notation, you're always going to do the inside first, just like when you plugged in the number. Right? You did this f of x machine first, got an answer, and whatever answer came out went into the second machine, and there was an output. So we did it with a bunch of numbers, and we found out that -4 was not possible. But you can also do it with different values. Like if I wanted to, I could plug in a k. Well, what would happen if I plugged in k into machine A? What would come out? Well, what did you do with the 3? How did you figure out what came out when you did the 3? You plugged in 3 for x, right? Did 2 times 3, 6 plus 3 is 9, and out came 9. So now what do? You plug in k. What are you going to get? When it comes out, you're going to get 2k plus 3. Now, when you had the 9, then you plugged the 9 in for the x, right? And you got 1 over 14. Now you have a 2k plus 3. You have to plug the 2k plus 3 in for the x, and you're going to get 1 over 2k plus 3, that's where the x was, plus 5. So you get 1 over 2k plus 8. Which is the same as, I could factor out that 2. K plus 4. What would happen instead of plugging in a k, I plugged in x? If I plug in x, out would come 2x plus 3 instead of 2k plus 3. And over here, instead of 1 over 2k plus 3 plus 5, I would get 1 over 2x plus 3 plus 5, which would be the same thing here, except you'd have 2x plus 8, which would be the same thing here, except you would have 2 times x plus 4. When I plug in x, I get an explicit equation for the composite function. And what that means is now, can you see that -4 would be the one that's going to be not possible? -4, although it went through machine A just fine, when it hit machine B, boom, it blew up. And you have to go buy parts and buy a new machine, and then at your work, they put up a sign that says, do not put any -4s in here. Any employee seen put a -4 into machine A will be fired on the spot. Because the -4 went fine into machine A, but then it hit machine B and blew up. And when we see the explicit equation, we can see why, because then we divide by 0. All right, we're going to skip over the construct the understanding, but there are some important definitions here. And here is an example of where some of these composite functions are used. Because when you look at things that you do, there's lots of real life examples which are functions of each other. The cost of gasoline here is a function of how much you use, right? The more liters your car uses, the more it's going to cost for gasoline. So cost is a function of the volume that you use. So we've got a function C of V. But the volume that you use is also based on how far you drive, the distance you go. So volume can be seen as a function of distance. The farther you drive, the more liters you're going to use up. Putting those together, it's pretty obvious that the farther you drive, your cost will also be affected. Because if the farther you drive, the more gasoline you use, and the more it costs to buy it, then you've got a composite function. So you could say that cost is also determined by the distance driven. And what this means is we could now make an equation. You have an equation that you could say cost is based on liters, but you could rearrange that equation to figure out exactly how much it costs per kilometer that you drive. And then you could figure out, okay, if I'm driving, 350 kilometers, I now know how much it's going to cost for me to get there. And businesses will use this because some businesses require you to have a vehicle for work, right? And it's easier for them to say, how much did you drive, than it is for them to say, could you go into your gas tank and measure how many liters are missing? That would be very difficult to do. So they give a certain amount per kilometer as a way to compensate. And these are called composite functions. And here's the notation that I showed you already. F of g of x, or f composition g of x. So we say f of g, and sometimes they say at, and I've also heard sometimes they use the word of again. So f of g of x, or f of g at x. A couple more examples we'll do, and then we'll get to example 1. So here's two functions. Okay? And again, the important thing that I've talked about already is you always start with the inside function and work your way out. Sort of like thinking about brackets. Do inside the brackets first, and then work your way out. So when I have f of g of -1, I first would say, well, inside the bracket I have g. Here's my function g. What happens when you plug in a -1? Well, according to this mapping, if I plug in a -1, what would come out of the machine? A 2. So g of -1 is 2. What that means is that if I was showing my work, I start off with f of g of -1, and then I would write, well, that's equal to f of 2, because g of -1 is equal to 2. Which means I now can go to my f of x machine and say, well, what happens if I plug in a 2? Out would come a 3. So then I would say this is equal to 3. You can also do composite functions from a graph. So here's two graphs. You got f of g of -1. Again, we're going to start with the inside function, which is the g of -1. And I'm going to write an equal sign here, and I'm going to go and I'm going to look at my graphs and say, when I plug in -1, here's -1 for an x value. If I plug that into g of x, can you see that that would be on my blue graph, would be right here. When x is -1, y is 2. Okay? Does that make sense? So f of g of -1 is the same as f of 2. And f of 2 says, well, now that's looking on my red graph. I need to find out when I plug in 2, what do I get? Well, here's 2. On my graph, I have 2, 3. So f of 2 would equal 3. And this is how I'd recommend doing them from a graph. Right? Look at the inside, figure out that value, find out what it is, and then write it out. That's going to, g of -1 is 2, so I now have f of 2. And then look at your graph again. Now you're looking at your function f and say, when x is 2, what's y? And when I plug in 2, I look at my red graph and I have 2, 3. So then I get 3. Now, they have in the textbook developed a much more complicated system for figuring this out. What they do is they drew the line y equals x. They figured the same thing. They started the same way out, where they said if you go up from -1, you're going to hit 2. I say it's much easier than next just to go to 2 and go up to your other graph and figure out what it is. I think that's really simple. What they end up doing is they add another line. They say, let's draw the line y equals x. Let's go from this dot and let's go straight over until we hit that line. And when we hit that line, go straight up until we hit the point 2, 3. I think that's a little bit more complicated than it needs to be. You don't need to draw that extra line. Once you can go up to your blue graph from -1 and find out 2, you're going to be able to go up from 2 to find out your value on your other one just as easy. Okay, so we're going to do example 1.